Welcome to lesson 7.4, the sine and cosine ratios. In the last section, we learned about the tangent ratio. Through our investigation and our examples, we discovered that the tangent of the angle theta is the ratio given by the opposite side length over the adjacent side length. We discovered that it didn't matter how big the triangle was as long as the angle in question remained the same. So in these two triangles, the angle theta is equal to the angle theta, which means that the ratio of opposite over adjacent is the exact same in the big triangle as it is opposite over adjacent in our little triangle. And again, that holds true no matter the size of the triangle as long as the angle remains constant. Today we're going to be learning about two other trigonometric ratios that can be explored and discovered just by using these same two triangles. We haven't used the hypotenuse yet in either of these triangles. It turns out that there are two other main trigonometric ratios. One is called sine, and the other is called cosine. The sine of angle theta is the ratio of opposite over hypotenuse. That means in these two triangles, as long as theta remains the same, sine of theta is the ratio that compares the opposite side with the hypotenuse. And in both of these triangles, that ratio will be the exact same. Opposite over hypotenuse of our small triangle will come out with the exact same number as opposite over the hypotenuse of our larger triangle. Cosine, which is cos for short, cosine of theta is the adjacent side over the hypotenuse. So the cosine ratio is equal to the adjacent side over the hypotenuse. And in both of our triangles, because theta is the angle in question in both of them, adjacent over hypotenuse will come out with the exact same ratio. These three ratios together, sine, cosine, and tangent, are called the primary trigonometric ratios. So the primary trigonometric ratios are sine, cosine, and tangent. Sine of theta is equal to the ratio between the opposite and the hypotenuse. Cosine of theta is the ratio of the adjacent over the hypotenuse. And the tangent of theta is the ratio of the opposite over adjacent. So go ahead and draw yourself a little diagram here. Label a theta and identify the sides. You've got opposite, adjacent, and hypotenuse. This little note here is enough to solve most simple primary trigonometric ratio problems. So go ahead and memorize that. Thankfully, there's a next easy way to memorize this. There's a mnemonic device, and it is SOHCAHTOA. SOHCAHTOA. The sine of theta is opposite over hypotenuse. The cosine of theta is adjacent over hypotenuse. The tangent of theta is equal to opposite over adjacent. SOHCAHTOA. So at the top of all of your homeworks for the next little while and the top of your tests, just quickly write down SOHCAHTOA, and that will help you remember which sides relate to which trigonometric ratio in order to solve for theta. So we can use each of these little equations to find the angle when we know the two sides. We can also use it to find one of the sides when we know one of the other sides and the angle. We found out it was really easy to plug this kind of thing into our calculator to find the ratio. For instance, if we wanted to find the tangent of the angle that's 25 degrees, we would just type in our calculator tangent of 25. And we'd get the ratio that goes with it, which would be equal to opposite over adjacent. We also discovered that we could, if we knew the ratio, just plug the ratio into our calculator using the inverse function of tan. So another note here that might be helpful is that in this case, theta is equal to the inverse tan of the opposite side over the adjacent side. And the same remains true when we're talking about sine and cosine. The theta here, the measurement of angle theta, is equal to the inverse sine, or sine inverse, of op over hyp, opposite over hypotenuse. And for cosine, of course, the measure of angle theta is equal to cosine inverse of the ratio adjacent over hypotenuse. So now we know how to find our ratio when we're given theta. We also have the skills and the calculator necessary to find the measurement of angle theta when we know any two sides in a triangle. Well, let's have a look at example 1. Example 1 asks us to find the three primary trigonometric ratios for angle theta and express the ratios as decimals, rounded to 4 decimal places. All the information that we need is here. We've identified a right angle triangle, so we know our primary trigonometric ratios will work. We've been given angle theta, and we've been given all the side lengths. All we need to do is identify which is the opposite, which is adjacent, and which is hypotenuse. Go ahead and do that now. And you can check the board to see if your answers line up with the answers that are given. Well, let's go ahead and identify all of our trigonometric ratios. We've got sine of theta, which according to SOHCAHTOA is opposite over hypotenuse. We have cosine of theta, which is equal to adjacent over hypotenuse. And we have tangent of theta, which is equal to opposite over adjacent. All I need to do to find my ratios is sub in the missing information. I'm tailing across. You're not really supposed to do that, but I don't have enough space to go vertically, so I'm going horizontally. You can feel free to do the same, or else use your space a little more wisely and go sine, cosine, tangent in your notes. But all I have to do is write opposite, which is 10, over hypotenuse, which is 26. Throw that in my calculator, and I will get approximately 0.3846. And we remember that it's important to keep at least 4 decimal places when we are calculating the ratio, because we're now going to use that ratio, or in subsequent examples we would use that ratio to calculate the angle. So this ratio needs to be very precise in order to get an accurate measure of our angle theta. Let's go down. This is enough for this answer. This is the sine ratio for angle theta in this triangle. Let's look at the cosine ratio for this angle theta in the triangle given. Well, we have adjacent over hypotenuse for cosine, so we go ahead and plug in our numbers. That's 24 over 26. Throw that in our calculator, and we get approximately 0.9231. Remember, we're just finding the ratios right now. We're not finding the measurement of the angles. For the ratio tan, we have opposite over adjacent, which is 10 over 24. Throw that in our calculator, we get 0.4167. And there we have the 3 primary trigonometric ratios for angle theta in the given triangle. B of example 2, they've thrown a slight change in it. All they've done is turned our triangle on us. So again, our first step is to identify opposite, adjacent, and hypotenuse. And we're doing that with respect to angle theta, remembering that hypotenuse is always our long side. So go ahead and label your sides. Check your answers on the board. And let's jump into our primary trigonometric ratios. Sine of theta is op over hyp. Cosine of theta is adjacent over hyp. And tangent of theta is equal to opposite over adjacent. Go ahead and plug in our numbers. For sine of theta, we have 6.4 over 7.6, which rounds in our calculator to approximately 0.8421. Cosine of theta is given as the ratio adjacent over hypotenuse, which is 4.1 over 7.6. In our calculator, rounded to 4 decimal places, is 0.5395. And the tangent ratio, which is given as opposite over adjacent, is 6.4 over 4.1. If we put that in our calculator, we have the result 1.5610. Now, if I was going to use these ratios to find the measure of angle theta, I might use the decimal rounded to 4 decimal places, but I could also just, with a better calculator and proper use of my brackets, I could throw this fraction into the calculator for my ratio, and that would give an exact answer. Be much more precise. Also, these are sine, cosine, and tangent, which are ratios. So even though we were working with centimeters in our side lengths, ratios don't have units. Ratios don't have units. A side length would, an angle would, but a ratio doesn't. Just as we could evaluate the ratio for tangent when we were given a specific angle measurement, we can do the same thing for sine and cosine using our calculator. Here we need to evaluate sine of 26 degrees. Well, if I turn my calculator on, all I have to do here is type in sine 26, enter, and I'll get the given ratio. The sine of 26 degrees is approximately equal to 0.4384, rounded to 4 decimal places. Go ahead and try to calculate on your calculator the cosine of 75 degrees, but we need to ensure that our calculators are in degree mode. When you've done that, you can check your answer on the board. And we'll move on to example 3. In example 3, we're going to be finding an angle using the sine and cosine ratios. And we're talking about Captain Jack and his ship. Captain Jack is navigating his ship to Port Harbor, located at point P, which is directly north of the ship's location, which is J. To compensate for an easterly current, he aims his ship for a point on shore that is 5 kilometers west of Port Harbor. That's point W, where Captain Jack is aiming his ship. Assuming that the point on shore is 20 kilometers from his position now, at what bearing must Jack head his ship? In order to complete this question, it might be helpful to have a better idea of what they mean by the bearing. On what bearing must Jack head his ship? Well, a bearing is a navigational term that describes a direction. it's generally expressed as an angle in terms of north, south, east, and or west. So let's go ahead and draw an angle here. And let's say we're heading this direction, and the angle between north and this direction is 25 degrees. Then the bearing would be north, 25 degrees east, which is read 25 degrees east of north. So there's our bearing. So this direction is N25E, which means 25 degrees east of north. If we were going out this way, and the angle between north and our direction were 70 degrees, then we would be heading 70 degrees west of north. We're not heading north, we're heading 70 degrees to the west of north. There's a little introduction to sea navigation using bearings to describe direction, and that's what we're doing with Captain Jack. In order to get set up for this word problem, let's set up a simplified diagram. So we've got W and the point P. The distance between them is given as 5 kilometers. And then directly south of point P, we have Jack's ship with J. And we have the third line of our triangle there, which is the distance between W and J is given as 20 kilometers. And what we want to find out is the measure of this angle right there, so that we can say that Jack is directing his ship so many degrees west of north. Because this is a right-angled triangle, we can apply our primary trigonometric ratios, either sine, cosine, or tangent. Well, what sides do I know with relation to theta, with relation to the angle that we want to find? I know the opposite, and I know the hypotenuse. So I can use the sine ratio to find out what the angle theta is. I know that sine of angle theta will be equal to opposite over hypotenuse. These are the side lengths that have been given, so I can sub in 5 over 20, which reduces to 1 over 4. Now all I need to do is throw this in my calculator by taking the inverse of the ratio in order to find theta. So I know, since the sine of theta is 1/4, or 0.25, the angle theta is going to be equal to the inverse sine of 0.25. I put that in my calculator, we get approximately 14.477 degrees. I'm going to round that in my final answer. Which tells us that Jack must direct his ship on a bearing of approximately north 14 degrees west. 14 degrees north of west should get him, judging by the easterly current, to Port Harbor. Section B of this example. Captain Jack is in communication with a submarine that is cruising at a depth of 400 meters below sea level. If Jack's radar tells him that the submarine is 500 meters from Jack, due north of his ship, At what angle is the submarine located with respect to Captain Jack's ship to the nearest degree? Well, let's draw a diagram to help us understand what's going on here. We have Captain Jack's ship on the surface of the water, and the submarine has told him that the submarine is at a depth of 400 meters. His radar tells him that the submarine is 500 meters from him. So let's say we're going down 400 meters, and the ship, the submarine, is about 500 meters from Captain Jack's ship. Well, we can form a right angle triangle with that information, and we know two of the side lengths. Now our goal is to find the unknown angle that relates the submarine's position to Captain Jack. So what we know is that the submarine is north of Captain Jack. So here we go, this way is north, and we want to find this angle. So my missing angle is theta, and I have two side lengths. So ka, toa. Which of these primary trigonometric ratios am I going to use to solve this problem? Well, I have the adjacent side and the hypotenuse. So I'll be using the cosine of theta, which is equal to the adjacent over the hypotenuse. The cosine of theta then is equal to 400 over 500. I can reduce that to a decimal, which is 0.8. Now in my calculator, theta is equal to the inverse cosine of the ratio, which is approximately 36.870 degrees. Therefore, the submarine is approximately 37 degrees north of Captain Jack's ship. And that is with respect to the line that is drawn from Jack's ship down to the bottom of the sea. So with respect to that line, the submarine is approximately 37 degrees north of Captain Jack. In example 4, we are asked to solve a right triangle. To solve a triangle means to find the measure of all the sides and angles. So in order to solve this triangle, we're going to have 6 pieces of information. We're going to have 3 sides and 3 angle measurements, and then that triangle will be solved. Well, let's start by labeling this triangle. We have the vertices A, B, C, and now we need our sides to be labeled. Well, sides are always named after their opposite angle. So if this is angle C, then this is side C, the lowercase c. If this is angle A, then way over here opposite is the side A. And if this is angle B, then over here we have side B. Some information that we already have, we know that C equals 20, and we know that the angle A measures 30 degrees. Well, we also know the angle B equals 90 degrees. So this third angle is pretty easy to find. Let's use our 2 known angles, A and B, to find angle C. We know that in any triangle, the measure of angle A plus the measure of angle B plus the measure of angle C is going to equal 180 degrees. In this case, we know that angle A is 30 degrees, angle B is 90 degrees. We don't know the measure of angle C, but we know that those added up are going to be 180 degrees. Now we have one equation, one variable. We can solve this simply by subtracting 120 from the right side of our equation. So the measure of angle C is 180 degrees minus 120 degrees, which is 60 degrees. So we have our three angles. A little trick here is also to notice that because it's a right angle triangle and it has a right angle, which is 90 degrees, the two acute angles are always going to be complementary, which means they will add to 90. So we could have solved angle C just by going angle C equals 90, because that's what's left after we take our right triangle out of 180, right angle out of 180, 90 minus 30, which equals 60 degrees, if you use your complementary angles property. So I've added my angle measurement of C to my diagram, and now it's time to find the side lengths. We already have one of the side lengths, so let's use that information and our primary trigonometric ratios in order to find the other two. Well, cosine is equal to adjacent over hypotenuse. So if I take the cosine of angle A, I've got my adjacent side, which is 20, and I need to find my hypotenuse, which is B. So the cosine of 30 degrees is equal to 20 over B. I can multiply both sides by B, which will get me the B of cosine of 30 degrees is equal to 20. And then to get B by itself, I can divide both sides by the cosine of 30 degrees. So B is equal to 20 over the cosine of 30 degrees. In my calculator, that is approximately 23.094. So the measure of side B is approximately 23 units. Well, which trigonometric ratio should we use to find A, the side length of A? We can really use any of the trigonometric ratios. We just have to pick the right angle and the right side measurements to go in the right place in our ratio. Let's use tangent. The tangent of angle A is opposite over adjacent, which means the tangent of 30 is A over C, which is 20. Well, if A divided by 20 is the tangent of 30, then it must be the case that the tangent of 30 times 20 is A. To think of it a different way, to isolate A, I need to multiply 20 by both sides. I need to multiply both sides by 20. So here, A is equal to 20 times the tangent of 30 degrees. In our calculator, that is approximately 11.547. I go ahead and write that missing information on my diagram as 11.5, and our triangle is solved. Here's a diagram that shows our completed triangle with angles 30, 60, and 90, and side lengths 20, 23, and 12. There are three primary trigonometric ratios. They are sine, cosine, and tangent. They are defined by the mnemonic SOHCAHTOA, and you can find any side length or angle measure of a right triangle if you know two pieces of information in addition to the right angle. To test your skills, here's your homework from your textbook, page 338, number 1 through 10, and page 344, numbers 1 through 11. You'll notice that this is overlap of yesterday's homework, but there are problems that you couldn't do yesterday and now you can. So there you go. Please work hard and come to class tomorrow with questions.